I'm Jez, and this is Arnaud, and we're here from Facebook to talk about abstract interpretation today. So I've been at Facebook working on the last 3 years on Android optimization, and we've used abstract interpretation extensively in the process.
So I manage the core compilers team at Facebook. So we build the infrastructure for our compiler tool chains, in particular the SPARTA static analysis engine that Jez will describe right now.
So today, we'll cover what abstract interpretation is, how and why SPARTA is being used at Facebook, how SPARTA is fast, and therefore why you might want to use it, and finally, we'll go over some examples on how you can use it. So at Facebook, we have many large Android apps that need to run on all kinds of devices, from high-end devices to low-end devices. As such, optimization is highly important. And since we are dealing with large apps, the optimizer itself must be efficient. Otherwise, you're just replacing slow run times with slow compile times. So the tool we use for optimizing is called Redux, which takes DEX bytecode, which runs on Android, and makes it smaller and faster. Now let's talk a bit about what it means to optimize something. So we want to make a program smaller and faster while preserving its observable behavior. And to do that, we need to be able to have a model of what its behavior is. And that is where abstract interpretation comes in. So in a nutshell, semantics are what kinds of behavior a program can exhibit. And we want to be able to model all of them. Now, we can't possibly simulate every single possible execution of a program because obviously that would be Turing complete. As such, we map concrete values, such as integers, into more general abstract values, such as intervals. And by representing more concrete states with many concrete states of one abstract state, the problem becomes more feasible. And then we simulate program execution in an interpreter using these abstract values until we reach a fixed point. So let's look at a signed domain for our first example. The signed domain enables us to answer questions like, does this function return a value that's always greater than 0? Does it return a value that's ever null? And so every element in the abstract domain represents one or more concrete values. In this case, our concrete values are integers, and the abstract values are simple intervals. So note that some abstract values are more general than others. By more general, I mean that one can represent all the values of the other and more. So in this example, is that a pointer? Yes. So in this example, the domain that says all elements greater or equal to 0 encompasses both the domain of 0 and the domain of elements strictly greater than 0. As such, we place it higher on the diagram. Every abstract domain must also have a top and bottom value. Top essentially encompasses all possible values, and it's another way of saying we have no idea what actual value this thing holds at runtime. Bottom represents no possible value. Usually it arises in the context of dead code detection, because if a program never executes a certain block, then none of the variables there get assigned any values. So now I'll demonstrate how we can use these abstract values to model a program's execution. On the left-hand side is a piece of code we stepped through, and on the right-hand side, we'll show the state of the program after each corresponding line is executed. So on the first line, we simply have A equals 0. On the second line, we assign B 1, but there is no abstract domain representing exactly 1. However, we do have the next best thing, which is that B is strictly greater than 0. Now we go into the if block, where B gets assigned 0. That's pretty straightforward, but now the next question is, what happens after we exit the if block? So we need a way to represent the value of B, and we have no idea whether the if block was taken or not. So we can look at the diagram and look at the next most general value that encompasses both values of B. So it's right above 0 and greater than equal to 0. Sorry, strictly greater than 0, and we get this. So for our next example, we'll progress into more general intervals. I'll point out first that signed domains are very simple intervals, and you can rewrite the earlier domain like this. I won't go into the exact diagram of the interval domain because it has many elements and it's a lot to take in. But in short, all possible domains are valid abstract values. And we are going to use the interval domain to illustrate what it means to iterate to a fixed point. So here we have a very simple loop that increments an integer. And we want to know, at the end of the loop, what possible values can a take? So our abstract interpreter is going to step through this. Now on the first line, since we initialize a to 0, a is simply the interval that contains just 0. Now we add 1 to it. And then inside the loop body, it becomes the interval that contains just 1. Now we go back to the top of the loop, because we don't know if we can exit it yet. And so we look at the last value of a and the new value of a. So the new value of a encompasses both the previous value 0 and the value in the body of the loop, which is 1. So a is now spanning from 0 to 1. And we repeat the process. As you might expect, a now goes from 0 to 2, and so on and so forth. But eventually, this terminates. So when we reach a from 0 to 9, note that in the loop body, a is still going to be from 0 to 8, because we know that the loop body is only entered when a is less than 9. As such, the next time we go back to the loop head, we see that a hasn't changed. And now we know we've hit a fixed point, and we are done with our analysis of the loop. So that's a very high-level overview of how abstract interpretation works. And now we're going to talk about how we can make it fast. So for those of you who are familiar with classic data flow analysis, this fixed point thing is also being done. But usually, they do a simple strategy of iterating over all basic blocks until we hit that fixed point. That means that any change in a single basic block causes the entire method to be reanalyzed over and over. And that's not very efficient. So really, what we want to do is to iterate in the innermost loops first, and then outermost loops, and finally the entire method. And to do that, we need to decompose the graph, the control flow graph, into these loops. And so we use this thing called Bordonko's algorithm for that. I won't go into the details, but conceptually, it is Tajun's strongly connected components algorithm applied recursively. So every time we detect a small, strongly connected component, we pretend that it is a single node, and then we search for the next largest SCC that contains it. And by doing this recursively, we eventually get all the loops of the program. I'll also add that soon SPARTA will have a parallel implementation of this. What this means is that instead of iterating through the blocks serially, we can break a program into individual loops and analyze them in parallel. This makes things even faster than it already is. The next optimization I'm going to talk about is Patricia trees. So in the example earlier of the loop, you saw that we needed to store the value of a at the loop header. And more generally, to know when we hit a fixed point, we need to store the program state at every basic block. Now this can get expensive, since a program can have many basic blocks and be very large. So hash tables are a common choice for representing these mappings. Lookup is fast, and it's all right for small programs. But as I said, for large programs, this is going to be inefficient because they're going to copy the hash table over and over for every basic block. And the thing is that most program states are going to be similar. Every basic block is probably going to modify maybe 2 or 3 variables, but there may be dozens or hundreds of variables per method. But fortunately, since most program states are similar, we can take advantage of this. We can store only the differences between the states using immutable Patricia trees. So here's a diagram of one such tree. So the keys of this tree are integers, and the values can be anything you like. So in this case, the integers are representing the register numbers, and here we are looking at an environment that binds register 5 to the string foo. Now suppose we wanted to change 5 to bind to bar. So this shows the environment that does that, and the gray nodes are the newly allocated nodes. So notice that we only need to allocate new nodes on the spine of the tree, and we can share all the other nodes with the other environment. What this means is that copying a patricial tree is effectively free if you don't modify it. And when you do modify it, it's only O log the total number of bindings in the tree. So I'll point out that not every app is large enough to warrant using trees. So small apps might actually benefit from hash tables. But fortunately, SPARTA makes it easy to switch between different data structures. So in fact, when Redux first implemented its register allocator, a hash table was faster for our liveness analysis. But 1 year later, due to growth in app size and optimization complexity, this was no longer true. Fortunately, it only took us 4 lines to move from a hash table to a patricial tree. This is because SPARTA provides very clear abstractions over the concepts of abstract interpretation and the implementations. And this move resulted in a 90% reduction in memory and a 60% reduction in running time, which is huge. All right, now I'm going to hand it over to Arnaud, who's going to talk about widening.
Thanks, Jess. So coming back to our previous example with this loop, so you might think that, okay, but absolute interpretation, there's nothing really so magical about it. If you have a loop, you essentially go over all iterations of the loop, and you will eventually hit the right interval, the right loop invariant. So what if the loop has a huge bound? You can't actually go on forever. So fortunately, absolute interpretation goes a little bit beyond that, and the theory provides the ability to make big jumps. So if you've seen that lattice of sign, and the lattice of generalized intervals that Jez just described, the actual lattice is very large, and in fact it's even infinite. And the idea here is to make to take some big strides in that lattice. So when you see it's not after a few iterations it's not converging, let's make a big jump, and then what absolute interpretation guarantees is that after a finite sequence of big jumps, you will eventually converge to a fixed point. So in this case, the most basic widening one could imagine is after a few iterations, it's not stable. So let's make a jump to the top of the lattice. And so in this case, so we have the interval 0, 9. Okay, it's taking too much time. Let's widen to top. And at the next iteration, so our invariant was top. That was describing all possible integer values. We go through the loop one more time. It still remains top, because incrementing all possible integers gives us the set of all possible integers again. Then we've reached a fixed point. So that's a way to get the analysis to terminate, even though we have arbitrarily complex loops. But then you might think, okay, that's very nice, but top doesn't give us much information. It could be all possible integers, and that loop seems pretty simple. And in fact, absolute interpretation provides you with the way of getting the right level of precision. Because once you've reached a fixed point with the widening, you can keep going on. You can keep analyzing the loop and getting more precise results. So if you see here that we reached the top during the iteration with widening, now what we can do, we can analyze the loop again. And when we enter the loop, we know that A is less than 9,999. And what the theory tells us is that the invariant we obtain is still a correct a sound approximation of all our possible concrete states. So technically speaking, it's no longer a fixed point. It's called a post-fixed point. But basically, it's still a correct approximation. So we can keep going on. And eventually, after a finite number of steps, we will reach another fixed point or post-fixed point. And in this case, this is the actual correct invariant, which describes exactly the set of all possible values the variable can take within the loop. So the algorithm with narrowing is a little more complex and costly from a computational aspects. It's not implemented yet in SPARTA, but it will be available in a future release, in particular when we'll provide more numerical abstractions. All right, so that's the theory. That's all very nice. But in practice, how do we use SPARTA? And is it as easy to use as we claim it to be? That's actually the title of this presentation, making abstract interpretation easy. So let's see. How do we code that lattice, the lattice of sign? So first of all, we just define an enumeration type that contains all the elements, all the symbols in that lattice. And then SPARTA provides an implementation for that lattice based on bit vectors. So it's a sophisticated implementation. I will not go over the details. I will refer you to the GitHub repository if you're interested in the algorithm. But it's a compact and efficient representation of the lattice. And so we have that type, sign lattice, which is essentially the overall structure, the framework, the bit vector representation of a lattice of that size with that elements. Then we need to encode all those relations in the lattice. So technically, it's called a partial order, but all those edges that you see in the lattice have to be encoded. So we define that particular encoding, the diagram, in a structure called SL here. How do we do it? It's very simple. We implement it in a very declarative way. We take each edge in the diagram, and we just add it to the structure. So bottom is less general than less than 0. Same thing for 0, for greater than 0. And then we know that 0 is less general than greater than or equal to 0. Same thing, so on and so forth. You got a trick. So that's all you need to do to implement that lattice. And a lattice structure has some particular properties. So it should satisfy a number of constraints. And the nice thing is that this implementation verifies that those constraints are actually satisfied. So it's not like you can implement any kind of lattice that doesn't satisfy those requirements. If the properties are broken, you will get an error when you execute that program. Now that we have our lattice, we need like a thin wrapper that allows us to express program properties using this sign lattice. So SPARTA provides the finite abstract domain constructor, essentially that takes any finite lattice and turns it into a finite abstract domain. So it just takes the elements, the lattice structure, the encoding is a bit vector implementation of the lattice, and the actual diagram that we just defined. Okay, so that defines a sign property for one variable, but we've seen that our actual program state is essentially a set of signs that all the possible signs for all variables in our program. So basically, we need to define an abstract domain that maps variables to signs. So we can do this using the again the constructors provided by SPARTA. We could use a hash table as Jez just described, or a Patricia tree. So in this case, we use a Patricia tree map abstract environment, and given our program variables, we map them to the sign domain. And what we obtain is the implementation needed to represent each program state at each program point. And that's all you need. So the code I've just shown is exactly all you need to write to get an efficient implementation of the sign abstract domain. Okay? So that's how we implement abstract domain. It's pretty simple. Now, how do we implement an analysis? How do we run that abstract domain over an arbitrary program? For this, we use a simple abstraction that's essentially a graph. So, as you can see, it's called a program interface. So, it's a general control flow graph with an entry node, an exit node, and edges. And it can represent the control flow graph of a method or the entire call graph of a program. And SPARTA is completely independent from the programming language or architecture analyzed. So you just need to provide a bridge between that interface and say your in the case of Redux, the Android bytecode, or it could be an abstract syntax tree, or let's say you want to analyze C++ programs, you have a bridge to the LLVM internal representation. And once you've implemented that bridge, the last step is to define the analyzer itself. And the analyzer is simply an instance of a fixed point iterator. So that the fairly complicated algorithm that will go over the program, that will take your program interface, your abstract domain, in this case the sign domain, and automatically go over all nodes, your method or your program, and perform the analysis. And in order to perform the analysis, you have to provide the semantics of your basic operations, of the statements, of how you analyze your basic blocks. And you have to implement two methods, analyze node and analyze edge. So in the case of a control flow graph of a method, a node is either a statement or a basic block, a sequence of statements. And you have to go essentially over all possible statements in your language or your internal representation and provide the correct semantics. So one example here, like if you analyze the statement that assign the value 0 to a variable, what you do is that you set the variable v, which is the left-hand side of the statement on that node, to the sign domain EQZ, which is equal to 0. And that's all you have to do. So on and so forth for all your other statements. And analyze edge is used mostly to analyze the branches or the conditionals. So when you go from one node to the other, so from one basic block to the other through a conditional statement, you have to perform some special operations. So you have to provide the semantics for that. So for example, here we have like a conditional that tests that whether a variable is greater than 0. And in this case, when we go to one node to the other, we must ensure that v is greater than 0. And it's done by essentially getting the abstract value, the sign of that variable, in the incoming environment, and forcing it to be greater than 0, using the meet operation, which is essentially an intersection. in the lattice. So whatever the sign was, we intersect it with greater than 0. And in particular, if the sign was something like negative, for example, less than 0, the intersection would be empty, would return bottom. So that means that this branch is unreachable. And as Jez described previously, bottom is very important as a way to detect unreachable or dead code through static analysis, to be able to actually statically infer that a condition is always true or false. And that's all you need. So again, if you want to see how this is implemented, you can look into the unit tests in SPARTA, or to have a more sophisticated examples, you can look at the code in Redux. And one very sophisticated example is interprocedural analysis, interprocedural concept propagation, as Jez will describe right now.
All right, so far, our examples have been using control flow graphs and basic blocks. But if you saw the program interface just now, we really only care about graphs in general. It doesn't care about what kind of nodes or what kinds of edges compose the graph. And therefore, we can actually swap out a control flow graph for a call graph and get an interprocedural analysis. And in fact, Redux is using just this to implement a powerful interprocedural constant propagation optimization. I'm not going to go into the slides for those because it's a lot more complicated. But you can find us on GitHub. So SPARTA is at Facebook Incubator/SPARTA, and Redux is at Facebook/Redux. And we have lots of code examples there. All right. Do you guys have any questions?
Thank you for your attention.
Yeah.